Hello friends, welcome to this session of R for Research Data Analysis. We will today learn linear regression. When we collect data, we want to find the relationships between different variables. The relationship can be linear, curvilinear or of other types. This relationship can be used to fit model, and using the model we can predict the values which we have not explored. In today's session, we will fit the linear regression model to data collected from a biochemical assay experiment. Linear regression is fitting a straight line equation in the form of y is equal to mx plus c. Here, y is called as outcome or response variable, x as input or independent or predictor or explanatory variable, c is intercept and m is slope. Both are collectively called as coefficients. In statistics parlance, this equation is expressed as y is equal to alpha plus beta into x. There is great mathematics behind this process. We will not go into it. We will learn to do it using R. There are 4 steps in statistical learning process: splitting the data in training and testing datasets, fitting the model to test dataset and exploring the model. This involves looking for the coefficient, significance and diagnostic plots. At this stage, we establish that our model is reliable to be used for further analysis. In the third step, we validate the model using test data. We predict the response value or y value using the test data and confirm whether the predictions are near to actual values or not. Let's go to RStudio and start coding. As I said earlier, the data which we are using is from a biochemical assay. Absorbance of series of concentrations of an analyte are recorded in triplicates. I have saved the results in a CSV file in this directory. We will import the data. For that, we will first set working directory. Set working directory is the function, inverted quotes, and the path will copy from the directory path. I'll copy this, bring it to RStudio, paste it here and change the slashes to forward slashes. And when we run that, working directory will be set. Here that working directory is there now. We will import the data in data frame df using function read.csv, and in inverted quote file name is required because directory we have set, and that file name we will bring from the folder. This file we are going to use. Copy and bring here, put the extension and run that. Data has been imported. We'll see the data head df, and first 6 rows are there, 3 columns are there. One is student column categorical, concentrations numeric, absorbance numerics, and we can explore it further using str function. Run that. We will attach the data frame using attach function, attach df, and we'll plot the numeric variables to see whether relationship exists and what type of relationship that is. And here straight line relationship can be seen in the plot. Core.test function will tell us the strength of the linear relationship. Concentration and abs will run that, and 99.28% correlation is there. And now we will start actual linear regression. For that, I will split the data. I will create the vector index is equal to, and using sample function I will sample the rows from the vector 1 to n row df, and 80% data I want to select. For that, I will use that round function, round 0.8 multiplied by n row. Rounding is necessary to make it integer. You can use integer function also for that, and rounding to 0 decimal, and in this bracket replace is equal to false. We don't want to repeat the row numbers. Now train data is equal to df, and from that index to select rows and all columns, therefore column index empty. The train data got selected. Test data df in square bracket minus index, that negative sign, to omit the rows which we used in the train data. Again row empty, we'll run that. Okay. dim train will tell us how many rows are there in train data. 26 rows are there in train data, and dim test will tell us how many rows are there in test data. 7 rows are there in test data. The next step is to fit the model, and for that we will store the results in lmmod using function lm, and first argument is formula that absorbance is dependent variable and concentration is independent variable, comma, and these two variables are coming from the data frame df. Not, we are going to use train data for this and run this line to fit the model. We will print the model to see coefficients, lmmod print, and these are the coefficients. Intercept is minus 0.07 and for coefficient for concentration or slope is 0.008693. Using generic function summary, we can explore it further. Argument is lmmod model object, and here we can see the residuals also. Residuals is the vertical distance between actual value and fitted value. Then coefficients, intercept is there, concentration slope is there. Then standard error we can see, and most important for us is the p-value. The p-value which tells us about significance of the results, and this p-value is very small, therefore our results are statistically significant. And another value important is adjusted r-square value, that is 0.98. This value tells us that 98% of the variation in absorbance is explained by variation in concentration, or concentration is responsible for 98% change in absorbance. Linear regression algorithm try to minimize the residuals, and during this minimization process it gets a perfect fit or best fit line equation. Here the equation of the best fit line will be absorbance is equal to 0.008693 multiplied by concentration minus 0.070289. The p-value for this model is 2.2 into 10 raised to minus 16, almost equal to 0. This says that this model is statistically significant. R provides diagnostic plots to explore the model, and plot function lmmod is the argument for that. And when we run this, we'll get the plots. Multiple plots are there, therefore it is asking to hit return or enter. Enter. The first plot is residual versus fitted plot, and residuals are very small. Residual is the vertical distance between actual value and fitted value. Next plot is the normal QQ plot, and our points are there on the diagonal. Residuals are, this is again an indication of the good fit. The third plot is a scale location plot. Again, random distribution of residuals is there, therefore we can see that our model is a good fit. And this Cook's distance plot is also showing that model is a good fit. Up to this point, we have proved that our model is sufficiently reliable for predicting the values. We will further validate the model by using the test data, and for that I will use the predict function, and we'll save the predicted results into pred is equal to predict, and first argument is the lmmod, and next argument is the data, that is test. And when we run that, results will be stored in the object pred. We'll see the result pred, and these are the results but not making the sense, therefore we'll add these results to the test data frame. Test scalar pred is equal to pred, run and see the test data set, and you can see here the actual value of absorbance is 0.02 and predicted value is 0.017. To confirm further that these observed value and predicted values are not different, we'll use ggplot and library ggplot2. I am calling ggplot function, ggplot, and first argument is the data set, that is test here. Second argument is aesthetic mapping, that x is equal to concentration, and y we will give in geom point function. Geom point AES y is equal to absorbance, and color is equal to red to distinguish, And for predicted values, geom point again, and AES y is equal to pred, color will be blue. And when we run that, we can see that these red are actual values and blue are predicted values. That's all for today. If you remember LM function and predict function, you can apply linear regression model to any two numeric variables for your data analysis. In next session, we will learn multiple linear regression. I have shared the code and data of this demonstration in description. If you like this video, please press the like button, share with your friends, and if you have not subscribed to my channel, please subscribe. Thanks for watching.